Hey, thanks everyone. Welcome to my talk about cloud catastrophes. So, who am I? I mean, I've just been introduced, so I'll skip all of that other than, no Twitter. So, cloud security is a big topic. There's a lot to cover, and this talk only covers like a very small part of it. And I try to be reasonably agnostic, but mostly my examples are from issues in AWS that we see, because that seems to be what most people are using.
Excuse me.
Sorry.
Can you just increase the volume of the
Sure. Maybe if I speak into that one. Is that better? How about that? How about now? Better? Better? Okay. Cool.
Just yell.
Yeah, okay. I'll just yell. That's good advice. So anyway, it's a big topic. There's a lot to cover, and this talk just sticks to a small subset of the issues that we've seen. And I've tried to build it around the theme of the differences between the cloud mindset, the cloud way of doing things, and like the traditional way of doing things. So one of the common things that you see is the hijacking of orphaned resources. So because cloud environments might have these global identifiers, everybody in the environment shares this global namespace, then you have this problem of these shared identifiers, and if somebody else takes your identifier, they can access your stuff. Similarly, cloud APIs are public, so cloud environments typically have an API that you can interact with, and often every aspect of that API is completely public, so whoever has the credentials can do anything that that user can do in that environment. And the final one I will talk about is these gaps in understanding of how the cloud auth models work. Cloud auth models each have their own kind of idiosyncrasies, and AWS particularly is quite flexible, and you can lead yourself into trouble with that. So first up is resource hacking. This is just a super simple issue that it's common-ish. Like you see it crop up in bug bounty findings. So we've got our organisation blah.com. They have their DNS, there's a CNAME for img.blah.com, and it points to an S3 bucket. And it's quite common to see that S3 bucket named after the DNS name. So that's all good. There's no vulnerability there. Nothing's really wrong with this situation as it stands. Where people get into trouble though is if someone goes and deletes that bucket, then now that name is available, right? And somebody else can now serve content from that bucket, and they're serving it in the context of this domain. So that could lead to access to the cookies of visitors to that website, and so on. So if you're doing this in the AWS console, it gives you a giant warning. It says, hey, are you sure you want to do this? You have to type in the name of the bucket to prevent you from doing it. But there's ways it could still happen, right? It could happen like if you're automating the creation and destruction of buckets, it could happen, along by that means. And, sometimes basic errors, even though the error is like a basic problem, the impact can be quite significant. I'm just going to move that down. So in this, can't win. So in this example here, this is from a bug bounty finding. We have an install script, and the install script is pulling the binary for the chat client out of the S3 bucket. Now the problem is the S3 bucket is unclaimed, so anyone can put a binary up as long as it has the right name. It's going to get run when the install script runs. So simple problem, reasonably large impact. So the key things that are happening with this is there's an identifier that's user controlled, another party is able to register that name, then there's the possibility that an attacker can hijack that and take that over. So there's a good list at the link on the slide that basically summarizes which services are hijackable and which are not. So S3 is obviously, that was my example, that's hijackable. Up until recently, like CloudFront was hijackable. I think it was last year that Amazon implemented a bunch of additional checks. So it's only in these edge case scenarios now that AWS is hijackable. But this list is worth visiting, because if you're using any of these things and you're automating the creation and destruction of these resources, then it's probably worth seeing if it's at least an issue that you should need to be thinking about. So what can you actually do about it if there's a potential for this vulnerability cropping up? What steps are worthwhile taking? So it's an issue caused potentially by like these dangling DNS resources that are pointing to something, and then that thing goes away. So, you know, creating some automation that reviews DNS and looks for like no result from DNS, then you want to find those and take action. So you may want to do that reasonably frequently if you're automating the creation and destruction of these things, or you may just want to run it periodically. So another issue that crops up with S3 buckets is sometimes people might have a publicly readable, writable bucket, but it's behind a CDN like CloudFront, and because it's behind the CDN, they think, hey, it's hidden, so no one can like push stuff to this bucket. So the problem with that is there's mechanisms to discover what those bucket names, and someone posted this on our internal chat the other day, that if you put like a question mark torrent on the end of the URL, you'll get a torrent file, and that torrent file is the actual name of the bucket. So you can, once you know the name of the bucket, the reason that's an issue is once you know the name of the bucket, then you can start probing that bucket directly on the bucket URL and find out if you've got read and write access or directory listing issues there. So the next issue is credential disclosure. So this is quite a common one. We do see this a bit in pen tests. This is where there's an issue such as server-side request forgery, and that server-side request forgery lets you talk to the metadata service, and sometimes there's credentials in that metadata service. So most of you probably know what server-side request forgery is, but just in case anybody doesn't, this is how it works. So we have an attacker who can make an HTTP request to the web server and tell the web server to go and fetch another resource. Now, depending on how that's set up, then that web server might be able to talk to a box on an internal network. And this is most useful when it's when the attacker can actually see the result. So sometimes it might be the case that the request goes out and you can trigger. You might see that it makes a DNS request for a server you control, but you never see the result, and it's less useful when that's the case. So if you're running on a web application and there's you wanting to know where to look for this, then these are the common places you're likely to see it. So anything that parses XML, potentially the XML parser, if it's an out-of-date version, it may have XXE vulnerabilities. So that's XML external entities, and that's where the parser actually will try and fetch a resource that you specify. So that's actually a feature of XML parsing, which is surprising and inconvenient sometimes. The other places you might find it is there's PDF conversion. Some web applications might have a mechanism, I want a PDF of this page, and some, depending on how that's implemented, it might reach out, make a HTTP request, use like a WebKit library or whatever to generate a PDF and give you that. And if you can specify the URL, then maybe you can fetch some internal resource using that. Another place to see it is application proxying, so API gateways or other proxy features within the application. Sometimes image uploaders will actually let you specify a URL. We saw, I think this was fixed, and this is like for Rails, there's a library called Paperclip for image uploaders, and that up until maybe last year, I think it was, would accept URLs, and you could get some level of SSRF with that. Those ones are less likely to be useful because frequently you don't actually see the result come back to you. And another one is webhooks. So that's a common one to see in web applications. It's a facility to create a new webhook, and maybe in the testing phase of that, you can see the result of the response come back to you. So why is this metadata service here serving up vulnerable information in the first place? So cloud services, they need a mechanism to distribute configuration to instances. They need a mechanism to give this information, like an instance, fresh instance spins up, it needs to know its IP address, it needs to have the SSH key that you are providing to it. So that's why the metadata service exists, and most cloud environments that I've seen so far at least have some kind of metadata service. Different ones have different levels of protection, like the Google one will check for a particular HTTP header, whereas the AWS one by default does not. So in this the trivial example here, just to walk us through what's going on, we have a web application. My web application will generate a PDF of any URL that I give it. So I give it the URL of the metadata service, and this time it's pointing to the security credentials for the role of that instance. And so, the EC2 instance merely goes off, makes that request, generates the PDF, and then serves it up to me, who's the attacker. So my PDF now has some useful information for me in it. It's got an access key, secret key, token, and I can import these credentials into my AWS CLI, and now I can do anything that role can do. So it's not always straightforward to exploit these issues. Sometimes you might have an application where the developers have they're aware of this issue, they've thought about it a bit, and they're like, we don't want this to happen, we're going to take some steps to prevent it. So this is an example of a real app. All the names have been changed, but this is what it was doing. It was like an API gateway, so it had two steps, like a configuration step and then an in-service step. In the configuration step, what we do is we specify our backend URL and our frontend URL. The backend URL is the API that it's actually hitting to retrieve the data, and the front-end URL is what the customers are going to be hitting. So once it's in service, then each time the request comes in, it does a DNS lookup for its backend and then sends the request off to that backend. So in the process of trying to exploit this, it's doing a sanity check. So in the host field, it says, put in the host, I put in 169.254, hope it, crossing my fingers, hoping that it's going to work, and it doesn't like it. So make a DNS entry for 169.254, and also that's not permitted. There's a bunch of other things that you can try, you can have the host that it goes and hits then do a redirect. So sometimes the client that's making the server-side request forgery will follow redirects automatically. So that's something to watch out for as well. And also there's various encodings, there's various ways to encode IP addresses, you can integer encode the IP address and a bunch of other kind of tricks like that. In this instance, it wasn't working. So we had a bit of a think about what we can do. So this is how it's normally working, this API gateway, just to step through it. So we are the administrator of this API gateway. We say, hey, please use a.com as our API backend. And it goes off and goes the API proxy, talks to the DNS server, and says, what's the IP for a.com? It says, hey, it's 1.1.1, and we go and check that that's reachable, and we talk to this API backend, and then the request comes back and says, all good. So now it's in service, and again, we're making this request to the API proxy. It checks DNS, it passes the request off to the backend, and it comes all the way back through to the user with a response in it. So that's how it's intended to be used. And this is our first attack attempt. So we put in, what's changed here is now it's because the attacker can choose the URL, they can also choose which DNS server it talks to. So in this instance, we say, hey, can you please use x.com? And our DNS server says 169.254, and the API proxy says no. So in our next attempt, what we're going to do is we're going to request for x.com, and it says, hey, now it's 1.1.1, because we changed our DNS entry, and it says, yep, that's reachable, okay, all good. Now, so now the API is in service, and it's it's passing on those requests from those public users. So this public user comes along and they say, hey, I want to have x.com/latest, and the request from the API proxy goes to my DNS server, and so now, because it's my DNS server, I can control what it returns. So the first time it returns 1.1.1, and the second time it returns 1.69.254. And so this is, when that happens, in this instance, what was in the metadata was basically the root credentials for the AWS environment. So that was a catastrophic kind of event for that service. So what are our options for mitigating this issue? There's a bunch of things you can do. The first one is super obvious, is just to avoid having like high privilege credentials in that user data, in the metadata URL at all. Often in the user data section, you might see, like, due to the way the application is like deployed and scripted, there might be high privilege credentials in there. So if that's in your metadata, then get it out of there if you can. So another mechanism to prevent it is you might be able to like make it so that you have an IAM policy that actually checks the IP of where that request is coming from. Now that is not the most flexible way to do it. So it might work for you if your developers are all coming over a VPN or all working out of the same office, but obviously you're going to need to keep updating that list of IPs. That's not the world's most flexible way to do it. This idea I thought was quite an interesting idea. So the reference at the bottom of this slide is someone from Netflix talking at AWS reInvent, and their idea was we're going to filter by user agent, because we know the user agents of the internal AWS API clients, we know what they look like, and we know what the CLI agent looks like, and if it's not one of those agents, we just drop the request. The reason that works is because when the web application is making the request, it's going to have like the curl user agent or whatever, right? So the attacker doesn't actually control the user agent at that point. Where this breaks down is if you get code exec on the box, obviously you're going to be able to change the user agent at that point. So it's not going to stop that, but it will stop just a straight up SSRF. And the same talk actually has another quite interesting idea as well, where you can trigger alerts from unknown IP addresses. So you get some kind of alert generated in CloudTrail or wherever you're doing your logging. And what's unique about this approach is the inbuilt AWS security tools they can generate alerts when the IP is from outside of AWS, but what this actually does is it's continuously building a list of known IPs, and it will trigger alerts if it's, because the way around the AWS tools is you basically just run the AWS CLI from it within an EC2 instance, right? And then it comes from Amazon IP space, and then you bypass it. So that's quite an interesting idea, dynamically building this list of known IPs. So the last thing I'm going to talk about is authentication and trust relationships. So in this, I got this scenario. So I got my rad dev shop, me and my mate Joe. We're a web development company, and we both have access in AWS because one customer. I mean, what do we got to lose? But time goes by. 4 years later, things are getting pretty hectic. We've got a bunch of customers, and we've got a whole bunch of developers. And so what we did is we went into the AWS console, and we enabled MFA on all our developer accounts. So it should be good to go, right? Well, if you do that, you enable multi-factor when they log in via the console, but there's still like the API keys. So these developers, they need that. They need to have admin access, right? Like they need to have wide-ranging access across the environment. It's not an option to segment them by customer or whatever, because they need to do troubleshooting, they're doing site reliability or whatever it is. They need that access. So what are the risks that, you know, a developer laptop is compromised or the creds are accidentally disclosed somehow? Surely they're not that high. Well, I mean, there's lots of ways the credential could be exposed, and you really just don't want to be like a game over event. I like this Twitter account, Bad Things Daily. So one of the scenario here is, you know, people are, you know, doing development and they're streaming it on Twitch, open to the public, and somebody alt tabs and their AWS key is like on the screen and published, you know, out to the internet instantaneously. So that would be a bit of a horror show. You wouldn't want that to happen. So in this example, what we're going to do is we're going to talk about using AssumeRole to enforce multi-factor for those CLI users. And the idea is like to do this like Bastion kind of account model. So there's an initial Bastion account. That account has no initial rights. And then we're going to use AssumeRole to elevate and gain admin rights. So it looks basically like this. And we're going to apply a policy to this group who can elevate and to allow them to assume role, and we're going to enforce a trust relationship requiring MFA before they can assume that role. So enable MFA in the AWS console for our admins. We did that. We create a group called can elevate, and we put our admins in this group. We're going to create some policy that grants those the members of can elevate the right to assume role. And we create a role admin that trusts members of can elevate and requires that they provide MFA. And then we need to set up the AWS CLI so it prompts for that multi-factor code. So again, that's what our scenario is looking like. So in the AWS credentials file, there's a user called MikeAdmin. And now we create a new config file and we add like a profile called admin, and it has three properties. It has this role ARN, it has a source profile, and it has an MFA serial. So it has references to these three things. The role ARN is that admin role. The source profile comes from the AWS credentials, and the MFA serial is my Google Authenticator, creates an ARN for my Google Authenticator token when I add that. So now when we want to do a privileged action, I mean, listing S3 buckets is not a privileged action, but this is just, you know, for sake of example. Now it will prompt me for my MFA code. As long as I specify I want to do this as an admin, it will prompt me for the code. So IAM policy is like super flexible, and there are lots of ways to like segment trust, and this way might not work for you, but it's just one way of doing it. But you do need to be careful because it's complicated. It's easy to tie yourself in a knot with it. So the best advice probably is to use the simplest model that works for what you're doing. So when you're looking at these IAM policies, sometimes it's not obvious what's going on, but other times it's pretty damn obvious. In this instance, we're granting the right to assume role, and it's granting it to star. So it's like anybody can assume role in this instance. This is something that a tool called Scout Suite will highlight, which is a tool to review AWS policy. But other times, reviewing this policy is not super easy. And the issues aren't always obvious. This piece of policy was intended to grant access to all S3 functionality except for like 2 delete permissions. So delete object and delete object version aren't permitted. Well, that's at least the intention. But actually it grants admin rights to everything. So it's not obvious just to look at this stuff. So a tool I've used in the past is this tool Cloud Mapper, which is quite useful for visualizing a complex environment. It has a feature called Web of Trust, and that can tell you which roles, which users can assume which roles. So that, I mean, in a simple environment, you can probably just do it through the console and you have a pretty good idea of what's going on. But if there's a lot of users and a lot of roles, and there's, you know, federation and whatnot, then that is useful. In this instance here, there's like, you can see Okta is the federation source. So in summary, these pools of global identifiers can lead to like resource hijacking. If you delete your S3 bucket or some equivalent resource, somebody else could potentially just register the same name and take control. And so the mitigation for that is really just to monitor these orphaned resources. The next one is like because these cloud APIs are public, if these credentials are disclosed, it can be a real game over kind of moment. And so it seems like a good mechanism is proxying access to this metadata service. However, whatever the most useful way to do that for you is. And the other one is the way these auth models work, that does require a bit of a mind shift. They all have their own kind of idiosyncrasies. So, enabling multi-factor for these CLI users seems like a really good idea, especially if a lot of people are using it. So it's cute to have a theme. That was the theme of my talk. But when I did a dry run of this, people were like, yeah, but what should I just go and do tomorrow? So this stuff is a little bit outside the theme, but this is like the super basics. It's a bit boring, but if you get these things right, then you can go and look for more complex issues. So, my first one that I would do would be, to use those built-in tools that are within AWS. So there's this credential report feature, so you can just go through and list all the users and see when the last time they logged in and whether they used their access key and whether they used their password, and if they didn't do it in the last 6 months or whatever, it's like, probably you don't need that user. So that's a good place to start, getting rid of stale user accounts. There's this security status page. You've probably seen the security status page whinging at you about not locking your root account and not activating MFA. If you make that page happy, then that's probably a good start. And the other one is in IAM, there's this Access Advisor tab, which is quite good for seeing what is the actual effect of this policy. So if you go to the Access Advisor tab, it will tell you what does this policy actually do, rather than trying to eyeball this obtuse kind of JSON. Another thing to look at is super basic again, but the security groups and VPC, ACLs. If you have, allow all rules are super obvious and easy to find. And with respect to S3 buckets, just the fact that people tend to be, or there's this tendency for things to be marked public that just don't need to be public. Now, last year I think, or earlier this year possibly, it's last year, that Amazon introduced this mechanism to globally across the account make it so that no bucket can be made public. So if you don't need public buckets, maybe that's a thing that's worth doing. Alrighty, I think that is the end. Thanks to OWASP and thanks to Insomnia.